Section 12.6 on cylinders and quadric surfaces. And so the point of this section is that we're going to discuss various surfaces in R3, in three-dimensional space. So far, we've talked about spheres, and we've talked about planes. Those are probably the two most important surfaces in three-dimensional space. But there are several others, cylinders and other quadric surfaces, and we're going to be needing these a lot in future chapters. So chapter 14 is going to use these a little bit. Chapter 15 and chapter 16, especially chapter 16, are going to use these concepts a lot. Okay, so let's just jump right in by talking about what a cylinder is. And let me just caution you for one thing right here. The book's definition of a cylinder is different than if I were to ask you right now, we were in person, I was kind of calling you and say, tell me what a cylinder is. This is going to be a different definition than the one you gave. So pay close attention to this. A cylinder is a surface generated by moving a straight line along a given planar curve while holding the line parallel to a fixed line. Okay, this is a mouthful. What's going on here? So first, let me talk about, cylinders, the classic high school or probably even middle school geometry version of what a cylinder is. So how do we draw a cylinder in, a normal high school geometry cylinder? Well, let's take a circle and then just take the circle and move it up and down. And so if I just take the circle and move it up and down like this, I'm going to trace out a cylinder, a normal high school geometry cylinder. Take a circle and so move this up and down. But or alternatively, you can think about this as taking a straight line here and moving the straight line around a circle here. So the idea here, move a straight line, the orange line, along the given planar curve. The planar curve here is a circle while holding the line parallel to the fixed line. So high school geometry cylinders are a special case of Thomas's calculus section 12.6 cylinders, but there's other things that also count as cylinders. So for instance, what we could do is, like it doesn't have to look like this. We can say, okay, our shape here, our planar curve is going to be a parabola. Our planar curve is going to be a parabola. Here's our fixed line. So what do we have here? You should start to see some 3D picture go on here where you have this very thin strip that goes along, goes off in this direction forever, goes off in this direction forever, has this fixed width to it. Here's an example of a cylinder where you have the planar curve is different than a circle. And also, I should say here, there's nothing to stop us from merely, from we could say, oh, let's not just stop here. Let's just make these lines go off forever in either direction. That is also completely a-okay. So let's go on here to a particular example here. Find an equation for the cylinder made by the lines parallel to the z-axis that pass through the parabola y is equal to x squared and z is equal to 0. So if I draw axes here, x, y, and z, y is equal to x squared. y is equal to x squared, z is equal to 0. So this is our parabola. This is our parabola in the xy plane. So what we, there's two different ways to do it. We can think about just starting to draw lots of these lines going like this. Or we can think about taking this parabola and translating it up and down. And so if we just keep drawing more and more of these parabolas and extend out these lines further and further and further, you get exactly the cylinder that comes from this construction. Lines parallel to the z-axis that pass through the parabola, y is equal to x squared, z is equal to 0. And so find an equation here. These points are all, what does a generic point here, x, y, and z, how can you tell that it does this? It just is going to satisfy y is equal to x squared, z can be anything. Y is equal to x squared, so there's a relationship between the first two coordinates. Z can be anything. So if right here, this might be the point in the x, this might be the point x is 2, y is 4, z is 0. But then up here, we just translate this to 2, 4, and 1, and we keep translating it, moving it up and up, up. 2, 4, 2, 2, 4, 3, 2, 4, 4, 2, 4, 5, so on and so forth. Z can be anything. So the equation of this cylinder is simply y is equal to x squared. Okay, so this is our first example talking about cylinders here. More generally, we have quadric surfaces. So a quadric surface is the graph in space in R3 of a second degree equation in x, y, and z. So we're going to spend the rest of these videos talking about more general quadric surfaces in terms of what, in terms of equations here and stuff like that. We're first going to do the special case of the form ax squared plus by squared plus cz squared plus dz is equal to e, where a and b and c and d and e are all constants. And so some of the surfaces we're going to learn about, there's ellipsoids, there's paraboloids, there's elliptical cones, there's hyperboloids.